Chapter 2: Interception of Information over Lands.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
Before we start the work, we need to configure a network interface. Only a system administrator can make these changes. We set the receiving mode for the network interface to promiscuous. Here is the first network card, ETH0. After configuring the network interface, we'll copy the software from the enclosed disk. Next, we will compile and install the software on the hard disk. The software compilation process can take a few minutes depending on the hardware configuration of the computer. We repeat this process for each of the required applications. After preparing the environment, we can begin to demonstrate the functions of the individual programs. The first step is to check which computers in our local network are active at the moment. For this, we use the Nmap scanner. Our aim will be to intercept the packet transmission to and from the computer at 192.168.1.245. To read the data, we will use the TCP dump program. To intercept information in star topology networks, we use the ARP packet falsification technique, or ARP spoofing. To achieve our goal, we will use the arp.pl script that we created previously. We will now copy it from the enclosed disk. Before starting the attack, we must enable the transfer of the packets that are not addressed for our computer. To do this, we modify the system file /proc/sys/net/IPv4/IP_forward, entering the value 1 into it. At last, we can run the arp.pl script we copied earlier, which will redirect the network traffic to our computer. The first call parameter is the IP address of the network gateway. The second is the IP address of the target. As we can see, the TCP dump program displays all intercepted packets on the screen. Now, let's try to intercept the traffic of a popular instant messaging program. For this purpose, we eavesdrop on the packets going through port 8074. As we can see, the operation has been successful. In the next lesson, we will discover the methods to intercept encrypted information. Chapter 3: Interception of Encrypted Data, Attacks on SSL Sessions.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
We will now create a temporary folder, which we will use to install the software. We then copy the tools we need from the disk enclosed to the hard disk. Next, we can start to compile and install the software. To perform our test, we will need to initiate a connection from another computer on the local network. In this case, it is the victim computer whose IP address is 192.168.1.3. This computer starts an encrypted connection with the example .com machine. As we can see, the simulated connection has been successful. We will now try to intercept the connection of the victim computer with the example.com host remotely. Let's check if the packet transfer is activated. If so, the operation will display the value 1 on the screen. We activate the transfer, entering the value 1 to the file /proc/sys/net/IPv4/IP_forward.
We still have to configure the IP tables for this rule to work correctly.
The request tells the system kernel to transfer all packets directed to port 22 of the example.com computer.
In order for the attack to terminate successfully in a switch-based network, it is necessary to use the ARP spoof program.
Finally, we run the SSHMITM application, which will help us to intercept the encrypted information. So let's check if the operation works as planned. As we can see, the SSH client informs us about a potential danger and prevents us from starting the connection due to the change in the server fingerprint. We'll delete the fingerprint database and try to start the connection with the server again. The attack has terminated successfully, what can be seen on the first terminal. In the following part of the demonstration, we will create a fake HTTPS server. The first step is to generate a certificate. We set a password to protect the certificate and other information that it will contain. This information will be available to the client, and so it should be consistent with the fake server. Finally, we can sign the certificate we have created. Now we set the redirect from the server we are spoofing. In this case, it is the paypal.com. We start the SOCAT program and observe the results. If it works, the information sent to the server will be intercepted. As we can see, the attack ended with success. We managed to intercept the transmission. Chapter 5. Hiding processes using 2.4 series kernel modules.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited. We will now get to know how the tools LS mode, INS mode, and RM mode work.
Let's copy the files required to implement the goals described in this chapter. Each core module is characterized by a specific structure. We will now compile our first module and test its function. As we can see, the module has been uploaded correctly. In the logs, the record, Hello World, appears. After unloading the module, we can see the character string, the end, in the logs that we saved in the code of our module.
Let's compile and test the test.c module as example.
It shows the current working directory. Using the strace program, we will now check which system function and application really calls. As we can see, the program setting and current directory uses the getCwd system function.
Let's try now to substitute getCwd calls with our own function. Our second module performs this task, changing the pointer in the syscall table as required. After uploading the core module, the value returned by the getCwd function has been falsified.
Now we will dedicate ourselves to hiding processes. Let's check which system function the PS program uses. Using the getDense function, the program lists the content of the proc directory that includes information about current processes. Our task will be to filter the structures of the different directories so as to allow a specific process to be hidden. This operation will be executed by our next module. Let's have a closer look at it and configure it before uploading. After uploading the module, the PID 916 process, in this case the syslogged, is not visible in the PS program. Additionally, we have hidden the /home/users folder. Everything has gone according to plan.
After unloading the module with the rm mode command, the situation returned to normal.
Chapter 6. Buffer Overflow Attacks.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
We will now copy the required files from the enclosed disk to the hard disk.
Here is our first example program. It shows the content of the int a variable, which is visible in the program code. Let's compile it. As we can see, after transferring the second argument of the call, the int a variable has been overwritten with the value 0x41 corresponding to the letter A. To discover how the overwriting of the int a variable was possible, we will now look at the program examples using GDB. As we can see in the case of the car buff 10 variable, the stack has been increased to 24 bytes, 0x18 in the hexadecimal system. In the case of the int a variable, the stack has been increased to 8 bytes. By transferring 32 A characters, 24 plus 8, to our first program, we have overwritten the variable of the int a variable.
The next task will be to overwrite the int OK variable, which controls access to secure resources. After transferring the long character chain, it was possible to crack the program. But how can we do this if the variable controlling access does not exist? Let's test our next example program. We will now use a GDB to find out what happens at the moment a program call parameter that is too long is transferred. As we can see, the program wanted to jump to the address 0x41414141, which does not belong to its memory area. Let's now try to tell the program to jump to the correct address, which will allow it to skip to the procedure of login and password verification. This will be the address 0x080484C7.
The address of the jump has to be written in reverse order, starting from the last byte.
As we can see, everything went as expected. We managed to fool the application. Now we will analyze another example to exploit using the shellcode. In this case, a ready address that we could transfer does not exist. We will need to create our own shellcode and add it to our program. Unfortunately, a shellcode containing indirect closing function calls is not appropriate. It is necessary to create a code containing system function calls. We will obtain a ready-made shellcode from the binary program image using a objdump tool. The final version of our shellcode looks like this. We will therefore use a ready-made exploit that takes advantage of the techniques we learned while reading this chapter. As we can see, the operation has been successful. We gained access to the shell. Chapter 7. Practical examples of remote attacks.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited. We will now copy the required files to the hard disk using the disk enclosed to the set. If we do not have binary versions of the programs used, we will now compile and install them in the system.
To start the compilation process, we give the make command. Finally, we install the Nmap program on the hard disk. We compile and install the netcat application.
We use the Nmap scanner to check the services available in the victim computer.
Now we will verify the versions of the services made available by the server, analyzing greeting messages on the specific ports. As we have an account on the server being investigated, we can check the configuration of the Apache server and the possibility of exploiting security holes. As we can see, it's possible to execute system requests through the PHP script. We will now check the content of the www service on the server we are investigating. It is the PHPBB forum version 2.0.8. Let's search the internet to find out about the potential errors in this software. We did it! By manipulating the value of the highlight parameter, it is possible to execute our own PHP request. Now let's try to create our own exploit using the error in PHPBB. For this purpose, we will now familiarize ourselves with the basic instructions for the Python language. Python commands can also be run outside interactive mode by creating a file that contains a request set. Python also allows us to use external libraries, for instance, ftplib. As we can see, we can easily perform operations connected to the FTP connection without worrying about technical details. The urllib library helps us take advantage of the error. Using it, we can easily generate queries to the HTTPD server. After preparing a query, we start the connection and read the information returned by the server. The content of interest to us will be located between the start and stop tags. Only this content will be shown on screen. We did it. Our request has been executed by the server. Now, let's try to use the file version of the exploit created. It should work equally well. Everything went according to plan. Now let's use the netcat program to create an independent connection with the server. The connection has been made correctly. The system kernel is version 2.420. Let's find out if it contains any errors. Voila! This version of the kernel contains a serious error, the local use of which can raise the privileges of a normal user. Let's search therefore for a file with the exploit and put it to use. After compiling successfully, it is time to start up the exploit. We did it. Thanks to the use of the technique of inject the PHP code and the exploit, we obtained full access to the system by granting ourselves administrator rights. Chapter 8: Heap Overflow Attacks.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
Let's copy the required files into the temporary directory. We'll now have a look at the program in the example. It uses a few memory areas depending on how data are allocated. Let's compile and analyze our program in the example. As we can see, the objdump program has specified all used memory areas. Thanks to the objdump application, we can also gain insight into every memory area and analyze the code located in them. Now we will familiarize ourselves with another example, in this case, operating only in the heap area. In the program, the brk function has been used to change the heap size. Let's check how this function works. The function determines the end of the data area according to the call argument endDataSegment. The sbrk function was used to obtain current size of the data area, which was called with the 0 argument. We will now check how the program is functioning. Let's now have a look at another example that we will use to demonstrate the overflow in the heap area. The overflow happened after a perimeter of size above 16 bytes was transferred.
The next example we will see will use the heap overflow.
The program copies the data transferred as a call parameter without checking their length. After entering a call argument, it was possible to display the content of a file other than the intended file. If the suspectable program is working with the privileges of the system administrator, it is possible to read any file. Now let's try another example to demonstrate the use of overflow in the BSS area. Let's try to change the course of the program in a way that instead of adding, it divides. As we can see, when transferring an invalid argument, the application ended with an error. The program tried to jump to an area that was not located in its address space.
We can check the address of the fdiv division function and change the course of the program.
We did it. Despite the add argument, the program performed the division operation, which is visible on the screen. Now we will use our own shellcode to take advantage of the error in the example program. Chapter 9. Format String Attacks.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
Let's look at an example of the use of format tags. As we can see, the printf function allows us to use many format tags described in the system manual.
The use of many format tags is possible thanks to the VA lists described in the stdarg help.
Let's check to see what happens if we don't enter the call arguments for the printf function. After modification, our program printed data located on the stack. By using format tags, we are able to read the program memory to the bottom of the stack. Our next example demonstrates this. To write the data, we will use the %n format tag. We'll now take a look at how this works. The %n tag causes the number of currently printed characters to be written in the int variable. In the subsequent example, we will discover how to write any value to the address indicated in the program memory. We did it. We wrote the value 5 at the address of the int_i variable. The value 5 corresponds to the address length increased by the dash sign. We'll now try to write the value 1000, 0x3e8, in the hexadecimal system to the int_i variable. As we can see, writing a relatively small value does not constitute any problem. We will now write the value 0x88664422 to the int_i variable. Unfortunately, we don't have the ability to write such a big value. The solution is the division of our address into 4 byte fragments. Let's do it. The address of our variable has changed, and it is therefore necessary to correct it. We did it. The 0x88664422 address has been written correctly into the int variable. In the previous example, we were writing an address whose every byte was bigger than the previous one. Now let's consider the reverse situation. As we can see, thanks to the manipulation of the specific bytes of the address, we managed to obtain the intended result. Let's take advantage now of our ability in a practical example. We obtained the address of the int variable controlling access to the secured resources. We'll try to change its value. It worked, but what will happen if in the susceptible program there is no variable whose overriding can help us? In the next example, we will discover how to execute any code by overriding the EIP pointer. We will now try to obtain the address of the copy of the EIP register for the main function. This will allow us to execute the indicated code immediately after terminating this function. As we can see, the copy of the EIP register is located under the address 0xBFFFF39C. Let's write the address of our shellcode to this location. We did it. Now let's try to obtain the same effect without using the GDB, taking advantage of the format string attack. After checking the address of our shellcode, 0x80495520, we can start to construct an appropriate format string. We write the address of our shellcode under the address of the EIP register copy, beginning from the last byte.
After performing the address correction, we were able to execute the shellcode. Let's look at another technique, overwriting the GOT section.
The GOT section, Global Offset Table, contains information on external functions used in the program. By overwriting the address of the printf function in GOT with the address of our shellcode, we will cause its execution. It worked. Now let's perform the same task using a format string, exactly the same way as in the previous example. As we can see, the operation has been successful. We can now use our abilities to overwrite the program destructor section DTORS. By knowing the address of the end of the destructor list, we can overwrite it with the address of the shellcode. We did it. The ability to write any address in the program memory made it possible to take control of the application. Chapter 10. Practical examples of format string attacks.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
We will now copy the required files from the disk enclosed with the set.
Let's unpack and run the susceptible application, the Shoutcast server.
After startup, on another terminal, we can begin to analyze the application behavior. By applying an appropriate format string, we will try to save the value in the memory of the susceptible program. As we can see, the program has been closed due to an attempt to write to an unavailable memory area, which we forced with the %n formatting tag. Let's continue our analysis in order to reach the address searched in the program memory. This time we entered tag quantities that were too big because the server didn't process our query. Let's now try using two independent queries. We did it. We have found the data transferred in the format string. We will use it to write the address of our shellcode. As we can see, the application of %34 $X tag will not be successful as the server filters this type of query. Finally, we managed to transfer 4 addresses that will serve to indicate our shellcode. Let's familiarize ourselves with the shellcode. It makes available the command line on port 7000. Let's test it. Let's use the objdump program to obtain an address that can be overwritten with the address of our shellcode. We have chosen the sprintf function. Its address in the global offset table, GOT, is 0x08064993C. As we can see, the substitution of the sprintf function with the address we gave causes the jump. It is here where we will write the address of our shellcode.
Let's take a closer look at a ready-made exploit that draws on our experience.
In the first query, we will transfer the address of the sprintf function and the shellcode. In the second, we will transfer the tags to write the shellcode address. It worked. As we can see, the program tried to perform a jump to the address 0x66666666, what caused it to close. All we have to do is determine the address of our shellcode in memory and to transfer it in a format string. Using the GDB application, we can view the content of the program memory. Our shellcode starts from the sequence \x31\xc0\x50\x50. We can search for it. As we can see, the address of the beginning of the shellcode is 0xbf3feee0. Now we can take advantage of it. The ready-made query is located in the modified version of our exploit. Our actions have been successful. We have obtained access to remote shell. Chapter 11. File Stream Pointer Overwrite Attacks.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
We now copy the files that will be used in this lesson. Let's take a look at our first example.
As we can see, the program is susceptible to the error of buffer overflow while executing the fread function. Let's try to exploit this.
After we copied 1,200 bytes of data into the buffer, our program terminated with an error. Let's investigate the core file to discover the details. The program closed due to an error in the fclose function that tried to refer to a forbidden address. The address we entered, 0x41414141 or AAAA, didn't indicate a correct file stream used by the fclose function.
Let's try to use the pointer of the standard input, stdn. Let's overwrite with it in the area responsible for the file structure, in this case 1040 bytes.
The last bytes of our file will consist of the address with which we will overwrite the stack frame, 0x41414141. As we can see, we have managed to force the program to perform a jump under any address in memory. Unfortunately, as we will soon notice, the use of this technique is affected by the presence of the return function in the program. In the case of the exit function, it was not possible to force the program to perform the jump. Let's now consider a broader usage of the file stream pointer. We can investigate the appropriate header file in order to find the file structure. Unfortunately, we didn't manage to find the function pointer. We'll look at a simple example using the debugger. We find an interesting call of the /io_file close function. We'll find out what is located under this address. As it turns out, our function exploits system call number 6, the close function. Let's try now to overwrite the /io_file_close address with the address 0x41414141. It worked, and we caused the program to jump to a location in memory of our choosing. Analyzing the fclose function call, we encountered the secret /io_file jumps. Let's try to discover something more by looking at the resources of the libc library. As we can see, the structure /io_file plus allocated to the file uses an additional structure /io_jump_t.
It is exactly the structure that we found during our earlier analysis of the std_n stream.
So let's take a look at the ready-made exploit. We modified the program slightly to discover the address of the buffer being overwritten. We entered the address in the code of our exploit. We did it. We executed the shellcode by overwriting the file stream. We gained full control over the program. Chapter 13. Exploiting the ICMP protocol.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
In this chapter, we will get to know how the ICMP protocol works. Let's start by learning about the basic tools, ping and traceroute. We'll look at the useful option of the ping program and see how they work. Thanks to the parameter -c, -s, and -t, it is possible to determine the number of ICMP packets sent, as well as their sizes and time to live, or TTL. As we can see, after determining the lifetime of packet number 2, we see the information we need on the screen. After investigating the route of the packet with the traceroute program, we discover why the packet has been rejected by the second node, radio. We can now test the option that will be helpful during the DOS attack. The first of them is the -I option, which determines the packet sending interval. Another option is -F, which causes flooding with large number of packets. This option is available only to the system administrator. As we can see, within less than a second we managed to send 10,000 packets. But let's try to improve our performance using a specially prepared program. We will now copy the files we need. Our program uses raw sockets to send packets. After properly filling in the IP and ICMP structures, the packet can be sent. We will find the description of the specific structures in the header files. Finally, after having filled in the structures, it is possible to create a raw type socket using the socket function. We will now check the functioning of our program. We should remember that to create a raw socket, administrator privileges are required. Each dot printed on the screen represents one sent packet. Let's save the output of our program and count the number of dots in the program. As we can see, within approximately 5 seconds we had managed to send almost 400,000 packets. Now let's consider the ICMP protocol for other purposes. This protocol is often used in backdoors. Let's have a look at examples. As we can see, the sending of the ICMP packet generates significantly fewer suspicious records in the NetStat program. To a hacker, this is a huge advantage. Now, we'll unpack and compile the netcat program that will transmit data in the next example. Our backdoor will create a raw socket that will analyze the packets being received. When it intercepts two packets differing in size by 1,337, it will start up the netcat program. As we can see, after starting up the backdoor, the NetStat program indicates the presence of only the raw socket. After having sent two ICMP packets differing in size by 1,337, a netcat application has been started that enables access to the shell.
Unfortunately, the connection with the shell is visible at first glance. To prevent this, we will use our next program. The client program will send a properly prepared ICMP packet containing the password and the name of the file to send.
While the server program, after registering an appropriate packet, will send the indicated data in the answer. Let's compile our programs and see them work. We have been successful. The server returned the content of the indicated file. This time the NetStat program has indicated the presence of only the raw socket. Chapter 14. Remote Identification of the Operating System.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
This lesson describes the ways to remotely identify the operation system version. We will begin the demonstration with the simplest solutions. Using the Telnet program, it is possible to check the version of the service working on the server. The first parameter is the host name. The second is the port. We will not always manage to guess what version of the remote operating system with this method. In this case, it is necessary to use additional tools. Let's copy them. After equipping ourselves with the right tools, it is time to unpack them, compile them, and install in the system. The compiling process can take some time, depending on the hardware resources available to us. Let's focus on the compilation and installation of the popular Nmap scanner. After the installation of Nmap, it's time for the Xprobe 2 application. The set of installation commands is identical. Finally, we compile the POF program. Having a complete environment, we can start the test. Using the Nmap program, we perform an example of scanning. Using the "-o" option, we can obtain the version of the operating system. As we can see, in the answer we can see discrepancies in regard to the real version. The application to determine the system version performs a series of tests, which compares with the signatures it possesses. Let's take a closer look at them. As we can see, the signature in the example on the first glance seems slightly illegible. The reader can find detailed descriptions on each field of the signature database in the handbook. Let's now test the function of the next program, xprobe2. As we can see, the standard startup of the program didn't return 100% of the information. We can improve the results slightly by defining the open and close ports of the server under investigation. This time the basic result is close to perfect. We obtained 97% probability. Each of the programs presented so far belongs to the active scanners. This means that to obtain the result, it generates the data itself. Next, we will have a closer look at the POF program. In contrast to the previous programs, it is a passive scanner. For the program to bring results on the network, an exchange of packets has to take place. In our case, it will generate traffic on an additional console. As we can see, the attempt to analyze the SYN packets didn't produce any results. Let's try to use the ACK and RST packets for our test. Finally, scanning with the use of the RST packets only brought near-perfect results. All the program signatures are located in the files pof.fp, pofa.fp, pofo.fp, and pofr.fp. Let's take a look at one of them. As we can see, the program database also contains records regarding Nmap. In this way, it is possible to intercept the scanning, which we can demonstrate immediately. The POF application is a universal tool. It can help us to identify the version of the operating system as well as to intercept a potential attack. Chapter 15: Net Filter and System Security Services.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
We will now check using Telnet which daemon SSHD version is installed on the tested server. So let's connect with port 22.
As we can see, we also managed to obtain very valuable information, the exact version of the remote system, in this case, FreeBSD.
This information is not always made available. In order to overcome this, we will use special software. Therefore, we will copy the files we need. We will now unpack, compile, and install the applications in the system. The compiling process will take a couple of minutes, depending on the hardware resources available to us. After around 2 minutes of compiling, the Nmap application is ready for installation. The installation should be made from the root level. Let's perform the operations for the POF program. After the software installation, we can start our tests. Let's check which system version is installed on the tested server. We managed to obtain information independently on the system version. The aim of this lesson is to demonstrate how the core modules that use the features of the NetFilter subsystem work. We will therefore learn to modify the behavior of the network stack, which will enable us to deceive the tools for the remote identification of the system version. But let's start by introducing a simple module that after uploading writes the information to the core logs. After looking at the example, we can proceed with using NetFilter. Our next module will have to reject all packets.
Let's familiarize ourselves with the structures we will use in our modules. This information is located in the NetFilter H file in the kernel sources.
The main structure of our module is nf_hook OPS. Let's have a look at it. Another important structure is sk_buff. It stores all packets going through the network device. Let's compile and test the functioning of our module. Before compiling, we will make a slight correction to the makefile file. As we can see, after uploading the module, all packets going to the device are being rejected. After unloading the module, everything returns to normal and the ping program registers subsequent echo reply packets. Our next module's task is to reject the packets on the ETH0 interface and to print the information about the event in the core log. As we can notice, all went according to our plans. Therefore, it is time to describe another example. Next module takes advantage of filtering the IP address and the port. By controlling these parameters, it is possible to reject only chosen files. As we can see, after uploading the module, the connection with port 22 was not possible. Our IP address 127.0.0.1 has been recognized.
Our next example has been extended by the modification of the parameters window and TTL for each SYN packet.
First, let's write the information on the fingerprint of the free BSD system. We will use this in our next example. Now let's test the functioning of the module. We'll see what POF returns before as well as after it uploads. As we can see, we managed to mislead the program and change the window and TTL values into the ones defined earlier.
The last example shows how we can change other packet parameters, enabling us to pretend to be any operating system.
Here we will use information obtained earlier from the signature database of the POF program for the free BSD system. We will now test the module. We have been successful. Our system has been recognized as FreeBSD version 5.1, although we are working in the Linux system. While it is true that the Nmap program didn't recognize us as FreeBSD, by changing the packet properties, we made identification of the system impossible. Chapter 16. Securing the system step by step.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
In this lesson, we will dedicate ourselves to an overview of basic issue of system security. Let's start with dividing the hard disk into partitions.
In order to maintain an optimal level of security, we recommend the division into the partitions //swap/var and /boot.
After having performed this division, we shouldn't forget about the correct settings of the administrator's password. The password shouldn't be too easy or too short. We recommended using passwords containing special characters.
Only the use of a sufficiently difficult and long password will allow us to secure our system optimally.
Now, let's proceed with setting simple rules for filtering the network traffic. We will use the script that we have prepared earlier. Let's copy the auxiliary files from the disk included in the set.
The startup of the firewall.sh script will cause the packets incoming on all ports to be blocked, with the exception of 20, 21 FTP, and 80 HTTP. We can check the set of the rules currently valid with the iptables command. After a preliminary configuration of the rules for the network traffic, we will now proceed with switching off the superfluous services. Therefore, let's analyze the /etc/inetd.conf file.
As we can see, at the present moment a number of services are available that we don't intend to use. We will switch them off by using the commentary sign.
In order for the changes entered to be visible, it is necessary to reload the inetd configuration daemon first. We do this using the command kill all hup inetd. To commend out the records of the daemon inetd configuration file, we can also use the ready-made script inetd.pl.
If the SSH service server is installed in the system, it is also necessary to use a secure configuration. After making changes to the configuration file, we must force the reloading of the program settings. Now let's proceed with the next, the verification and configuration of the programs which the SUID attribute. We will use for this purpose the sup.pl program. It will generate a list of files that work with administrator rights. After a moment, the SUID text file has been generated which contains the applications it has found. Let's have a look at it and make modifications. We update the settings using the sup.pl command. As we can see, the S attribute has disappeared from the string representing the access rights.
If we don't want every user to be able to change his own password, we delete the SUID attribute from the /usr/bin/passwd program.
The last operation we will perform is to determine the secure terminals where the administrator can log on locally. After performing the basic configuration, we shouldn't forget about the kernel of our system. The current kernel version is located under the address kernel.org. So we have now reached the end of the basic system configuration. Advanced security mechanisms will be presented in Lesson 18. Chapter 17. Security Scanners.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
In this chapter, we will look at popular security scanners. First, let's copy the programs to the hard disk. We'll now compile and install the individual programs, beginning with Nmap. The compilation process can take a couple of minutes, depending on the available hardware resources. Finally, we will install the program on the system using the root account for this purpose. As we can see, Nmap has many options. Let's familiarize ourselves with them using the manual available with the system. We will investigate the first option, -ST. It determines the standard type of scanning using the connect system function. The next kind is half-open scanning with the SYN packets. In order to take advantage of this type of scanning, we will use the -SS option. The next method corresponds to scanning using the FIN packets, with different flags set depending on the option chosen. However, we should remember that this kind of scanning can be ineffective for Windows systems. The next parameter is -SU, which corresponds to scanning with the UDP protocol using IC-MP packets. Also worth mentioning is the -SP option. It determines if the scanning target is presently active. By using the star sign, we can scan the whole subnetwork. Using the -SV parameter, we can determine the exact service version working on a specific port.
The -S0 parameter uses scanning with the IP protocol. The scanner sends IP packets that not have the header of another protocol and expects the answer.
Another parameter is -SA. It allows us to set the port filtering. This technique uses the ACK packets. The -SW option corresponds to the scanning technique with the window size of the TCP packet. It allows us to define the port filtering through a firewall. The -SL option serves to generate the list of host names or IP addresses without performing proper scanning. Now let's proceed with the installation and configuration of the next application, Nessus. The program compilation can take some minutes, so patience is required. As we can see, many compiler warnings are being generated. However, this does not influence the positive termination of the compilation. Finally, after around 6 minutes of compilation, the program is ready for use. We still have to generate the certificates and the user. After terminating the configuration, we start up the Nessus server and wait for all the plugins to upload. After logging in and accepting the certificate, we have access to a series of plugins that we can use during scanning.
We select only these plugins that will be useful during scanning. This will significantly shorten the test execution time.
Finally, we enter the name and IP address of the scanned computer and define the scanning method. After a moment, the results of the test are available. Let's have a look at them. After familiarizing ourselves with the scanning results, we can save ours in a report in one of the many available formats. Next program we will have a look at will be Nikto. So let's unpack the application. Nikto is an extended scanner of the www server. It allows over 3,000 errors in the server configuration and in PHP in CGI files to be detected. Before proceeding with scanning, it is a good idea to update the program database. We use the update parameter for this purpose. The update can take several minutes depending on the capacity of the link we have at our disposal. After having updated it, we can proceed with testing the functioning of the program in practice. As we can see, the scanner has revealed many errors in the configuration of the software that works on the www pages server. Chapter 18: Improving Security with Patches.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited.
In this lesson, we will get to know the core and compiler patches that improve the level of system security. Let's copy the necessary files onto the computer hard disk. We will start by unpacking the core sources and putting the GR security patch, PAX, in place. To install the patch, we will use the patch command. We can therefore proceed with the most important task, the configuration of the PAX system.
To make the task slightly simpler, we will upload the alternative GR security configuration file.
We can finally proceed with the patch configuration. A description of all available options is included in the handbook. After terminating the configuration, we save our settings and leave the configurator. The next step is the compilation of the new core and all modules. We will therefore perform a series of make commands.
After a couple of minutes, depending on the hardware resources of the computer, the new kernel is ready for installation. Let's make the appropriate entry in the Lilo configuration file to make the new kernel visible during the start.
After reloading the boot manager, we have to restart the system using the reboot command. After the new startup of the computer, it's time to test the functioning of the patch. We will use the PAX test tool set for this purpose. As we can see, by using Cybersecurity, the majority of attacks has been detected. Now let's look at another patch. It's time for the GCC compiler. We will now unpack the compiler sources that we copied earlier and install the Stack Smashing Protector patch. We have now to configure and compile GCC. A new version of the compiler will be available in the /usr/pp directory. After compiling, it's time to install the new compiler in the system. Now we will test Stack Smashing Protector on an example. As we can see, after compiling the program using the old version of GCC, it was possible to overwrite the stack frame.
Let's now check how our program will behave after compiling with the modified GCC version.
As we can see, the attack attempt has been noted in the program and has been terminated before the stack frame could be overwritten. By default, the patch secures only the character tables. Let's check this on our next example. To make possible the protection of other types of data as well, we must use the fstack protector all option during compilation. As we can see, the attack attempt has been detected. To check how Stack Smashing Protector works, we will analyze our program with GDB.
Control of variable overriding is possible thanks to the application of guards. We can ascertain this by following the program execution step by step.
In the case of normal program performance, the guard variable is not overwritten. After an argument that is too long has been transferred, the guard variable is overwritten, and the comparison occurring in the program body indicates the occurrence of the attack. Now let's look at the libsafe library. It is a safe equivalent of the standard libc library. As we can see, the next example uses the dangerous gets function, which is also signaled by the compiler. To add the libsafe library to each program being started, it is necessary to modify the ld_preload system variable. As we can see, our program ended without errors despite using the dangerous gets function.
Chapter 19: Intrusion Detection Systems. The unauthorized reproduction in whole or in part of this publication in any form is prohibited. We will now copy the tools we need from the disk enclosed with the set.
Before compiling the Snort application, we must first prepare the libp cap library. Let's take care of it. The next step is the compilation and installation of the Snort program. The program compilation process can take a couple of minutes, depending on the speed of the computer. After terminating the compilation and installation in the system, we can proceed with the configuration of the program.
Finally, we start Snort and observe the results on the screen. The port 22 has been excluded in order to make the report's content possibly readable.
As we can see, the exact content of each packet is shown on the screen. After interrupting Snort, general statistics of the registered packets will be shown. Additionally, each packet has been saved in the assigned directory. This is a very useful function. The invaluable characteristic of Snort is the ability to create rules according to which the program will write or discard the packets. Let's take a look at an example rule file and analyze its structure. A detailed description of the creation of rules is to be found in the handbook. Let's make a small modification of the rules file and check its function. As we can see, the rules defined earlier have been adapted to events occurring in the network. Let's now test the function of another program from the IDS family, ports entry. After a moment, the program is ready to work. Let's check its function by detecting the TCP port scanning. As we can see, the program registered the scanning attempt and efficiently prevented it from carrying out a potential attack. Chapter 12. Errors on the system kernel level.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited. Let's copy the files that will be used during the demonstration.
We should remember the characteristics of the buffer overflow attack. For this purpose, we'll look at a simple example.
Using the ulimit command, we can set core file to any size and check the function of our program.
As we can see, the stack frame has been overwritten with the argument we entered, due to which the program ended with a segmentation error. Let's now take a look at an example of a core module and try to take advantage of the buffer overflow error existing in this module. We will now compile and upload the susceptible module. These operations can be performed only by the system administrator. From the moment the module is uploaded, a current system uptime is included in the file /proc/jifffies. Let's see what will happen if we write data to the file that the program doesn't expect. The change of the file content should be visible in the core logs. As we can see, after writing data of more than 16 bytes to the file, a core exception has been generated. Since we are able to control the core module function by changing the EIP pointer, we'll use the shellcode for our purpose. Let's modify the previous makefile file to compile the shellcode.
After changing it into binary form, our shellcode looks like this.
Let's use the ready-made exploit code containing the shellcode and write its data to the file. It worked, and we control the execution of the susceptible module by creating a child process with system administrator rights. Now let's consider a real example. We know about the existing of an error in the implementation of the Bluetooth protocol. Let's check it. The error is in sock_create, the function responsible for the creation of a socket. By manipulating with proto-variable, it is possible to execute our own code. Our shellcode should raise the privileges of the process currently started up, so let's modify it. Here is the binary form of our shellcode. It will be used in the body of a new exploit.
The next step is to discover the address of the BT prototable. We'll try to find the address of uploading the susceptible module and modify the exploit.
We did it. We discovered the address by analyzing the system kernel. Now we can check the functioning of our exploit in practice. In this way, we obtained unlimited access to the system. If the BT_prototable address is missing, we can use the force method. The address of the search table has been found. As we can see, the operation has been successful. Chapter 4. Entering the system by the back door.
The unauthorized reproduction in whole or in part of this publication in any form is prohibited. This lesson describes ways in creating backdoors in computer systems. We will start simply by modifying the file /etc/passwd. Before making any changes, we create a backup copy of the file /etc/passwd.
Now we will add the user John, who will have administrator privileges and will be able to log in without a password. As we can see, the login has been successful. The user John is being recognized as root.
Now we will modify the configuration file on the server inetd/etc/inetd.conf.
Let's check which record format is valid in the configuration file of the program. Now we will archive the file and create an entry that will make the system shell available on port 901, the SWAT service.
Before the connection can start, we must reload the inetd settings.
As we can see, we have gained remote access to the system without needing to log in. Let's combine the methods we have learned and create a backdoor that will automatically set up an administrator account after detecting the connection on the chosen port. We will now copy the required programs from the disk and continue with their compilation and installation.
As we can see, the user John does not exist in the file /etc/passwd at first, but after the back program starts, he is added automatically. Now let's modify the inetd configuration daemon and reload its settings. We did it! After connecting the port 901, the John account has been created. Now we will try to achieve the same effect by using the ICMP protocol. So let's compile and test our program. As we can see, after receiving the needed ICMP packets, the user John has been created. Chapter 20: Attacking a Web Server. The unauthorized reproduction in whole or in part of this publication in any form is prohibited. We will now copy the required files from the disk enclosed with the set.
Now let's have a look at our first example. It will demonstrate 5 methods for remote execution of a command on the PHP script level. We'll copy our script into the target server and see how it works. As we can see, we managed to execute the command from the script level. However, it often happens that this possibility is blocked. To block dangerous functions, it is necessary to edit the PHP ini file. After restarting the Apache server, the configuration changes should be applied. The next example we will look at allows us to list the content of the directory and to read the indicated file. To limit access only to a defined area, it is necessary to use the open_base dir option. We'll modify the php.ini file. As we can see, after updating the settings, access to the directories has been blocked. The next example demonstrates how the function built into the PHP script code works. Our next task will be to rewrite this function in the C language and to use the module we created by doing this. After compiling, we obtained the binary form of our module with the name test.so. To use our module in the script, we use the DL function. As we can see, the module could not be uploaded. We will therefore make a small modification to the path of our module. It worked, and we have taken advantage of the function available in the external module created earlier with success. The next task will be to prepare a module that will allow us to list a directory and to execute any command. Before starting the compilation of a module, we will modify the makefile file. Let's upload the script code and the binary form of the module into the server and check its functioning in practice. As we can see, it worked as we wished. We have successfully read data from the indicated file and listed the directory content. To exclude the possibility of loading external modules, we add the DL function to the list of blocked commands. Let's try now to use our module on another server. As we can see, the module couldn't be uploaded due to the lack of compatibility with the version of PHP in use. We need to compile the module without using the debugger symbols. An alternative solution is the use of macros to deceive a compiler, which will allow us to force the upload of the module. With the right PHP version, we can compile the module using the required settings. After configuration, we can proceed with the PHP compilation. This operation can take a couple of minutes. Finally, we install the new PHP version in the system using the make install command. With the new PHP version, we will now make a small change to the makefile file, compile our module, and copy it to the server. As we can see, all went according to plan, and the code of our module has been executed correctly. Let's now try to deceive the compiler by using the macros mentioned earlier. To do this, we will modify the module code. We've been successful. The use of the appropriate compiler macros allowed us to execute the module correctly. Another obstacle we can encounter while using the external modules is the safe mode. As we can see, switching on the safe mode effectively prevents us from using our module.
We can obtain information on the PHP environment options using the PHP info function.
If all the possibilities known to us have been switched off, we can check the susceptibility of other modules offered by the server. An error in the curl module, for example, allows us to remove the limitations introduced by safe mode and read the file content. Another method to circumvent the security precautions is the use of the CGI scripts. Before starting up, our script should possess the executability attribute. We assign this with the chmod command. We did it. So let's try now to use the ability to start up CGI programs on a more ambitious example. If we lack access to the shell, we can also use the CGI script in the compiled file.